Welcome to lecture 23, part 2 for CS6 CS2 classes. Can you guys tell me till where did you all, understand in the previous lecture? So I was talking about some graphs, and I think while I was talking about this difference graph, the connection wasn't that well. So let me just explain this again. Were you guys able to understand what I explained up here? Hello.
Yes, ma'am. This we understood.
Okay, good. So what I have done now is I'm just plotting the autocorrelation function for this graph and this graph. So I can clearly see that there is a trend in this graph, right? Now, if you look at the autocorrelation function, the correlogram which we have plotted here, you can easily see that it is decreasing in Yeah, so we can easily see that these bars are tapering down, but they do not cut off to zero, right? They're decaying slowly and gradually. So if you observe such kind of a autocorrelation function, you know that there is some dependency, there is some sort of a trend in the graph. So it might either be, an increasing or a decreasing trend. So you will observe such a graph where your ACF is decaying gradually. So the very first instinct that should be is to difference the graph. So this was the graph, this was the ACF of the price. And now what you do is you difference those prices, and if you plot the ACF, you get something like this, which clearly is random. I mean, you can see that there is no trend and there is no decaying as well. It directly cuts off to zero here. So that's the way to, guess a stationary time series as well. So you can either look at its plot, then you can plot the ACF to have some more confirmation on the idea that you already have about the time series. And also the next thing that you can do is you can plot the histogram. So when I say that my model or the process that I want should be a stationary process, so I know that the series that I'm looking at should have a constant mean and a constant variance, which generally is the case for the normal. So you can also plot the normal, and upon it you can project the model's histogram. So let's say what you can do is something like this. So you just plot a normal first, and then, so this is some random normal distribution. And what you do is whenever you plot this normal distribution, you allocate it the mean and the variance of the data that you have at hand. And then you also plot the histogram. So if it looks something like this or like this, then you know that, it certain kind of it's the normal distribution that is stationary. So this can be one of the ways to identify whether a model is stationary or not. So let's say if you observe a histogram, which is something like this. So it takes higher values and then it just takes values like this. So you know that this is most likely to not be a normal distribution, right? And that is how you can see that, this kind of a series is a non-stationary series. And that is what you have to be aware of, because you know that only once you figure out whether your series is stationary or not, then and then only you can use the models. And you can use the models only if your series proves to be a stationary series. And what are the hurdles that can be for a series to be stationary? One, it can follow a trend. Maybe an upward trend, maybe a downward trend. It could be a deterministic trend where it always increases by a certain amount, or it could be a stochastic trend where you don't know, it can increase or decrease over time. But the only thing constant in a trend is that you can see that its mean will change each and every time. So what do I mean when I say that its mean will change each and every time? So when I'm saying that its mean will change each and every time, what you do is you have this series, right? And you can chop this series in some particular intervals. And you figure out the mean for this, for this, for this, and for this. So you can clearly see the mean will be here, 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 and then up there somewhere, or maybe here, right? So you see that there is an upward trend. The mean is increasing. So there is a change in the mean. So we know that whenever we observe a trend, there is a possibility that the mean is going to change over time, which is not the condition that a process needs to satisfy for it to be, be able to justifiable as a stationary process. So now we will have a look at some of the techniques that we can use to detrend a process. And when I detrend a process, and if after detrending my process becomes a stationary one, then that process will be called as trained stationary process. So now let me just write the heading, and let us start with, trying to see how we can remove a linear trend from the process. We'll have a look at the methods that we have to remove the non-linear trends as well. But let us start with removing linear trends. So we'll discuss some methods from, so we'll actually discuss a couple of methods, but not all of those methods will be suitable to all of the time series. So you have to have a look at the time series and see what kind of a trend is there. Even if it's a linear trend, is it a seasonal trend, or is it just an upward trend or a downward trend? And depending on that, you can use the method that you would, use to detrend the series that you have at hand. So now the very first method is least square trend removal. This is actually one of the easiest method to remove the least square, to remove the trend. So I have my first method as so what happens in least square is, let's say you have some time t and you have a process xt here, and you have observed some data points. There might not always be, a nice club. So you have observed these data points. So what you will do is you will fit a linear regression line to this data to, figure out what's the trend in the data. So if I were to fit a line, a linear least square line here, I would get something along the lines of this, right? So what in essence I'm doing is I'm defining, let us say I have a process xt here. So I have a process xt here, which is a trendy process. And what I can write for this is, let us say that my trend is a deterministic sort of a trend. So I have alpha as the mean of xt, and then I have bt plus yt here. And yt here is a zero mean stationary process. So this is kind of acting as a residual here. And we see that the trend setting part for this xt is this. I know that as and when I increase my t, this b is going to increase as well, which in turn will affect my expectation of xt, right? So what I do is I will take those residuals and I will choose to minimize the sum of those residuals, and I will fit the line of the best fit. And this is what will give you a proper straight line. But that's not all, right? So sometimes what happens is you can choose to have this line, and then what you do is you observe the differences between these values. So you observe these differences, right? Here there will be no difference, here there will be 0. And then these will be the data point that you will be looking at, right? But sometimes what happens is, let's say if you are given some random walk. Let us say I have a random walk which is something like this: xn minus 1 plus zn, where my zn can take values plus 1 or minus 1. So it takes plus 1 with a probability of 0.6 and it takes the value minus 1 with a probability of 0.4. So what do you guys think this kind of a process will be? Let us see what the data tells us. So the very first thing is to check whether it has a constant expectation or not. So what I will do is, I'll have expectation of xn as expectation of xn minus 1 plus zn, which will be expectation of xn minus 1 plus expectation of zn. And now I know that my expectation of zn is not 0. So if I were to calculate my expectation of Zn, it will be 0.6 minus 0.4, which is 0.2. So this will give me something like expectation of xn minus 1 plus 0.2. And here I have expectation of xn. So you see, each and every time I take the expectation, it is going to increase by 0.2. Or I can easily, substitute this again and again here, and I will get the answer as 0.2n for expectation of xn. So you clearly see that this expectation is not constant over time. So the process that I have just written here exhibits a trend, some sort of a trend. So now what we can do is, you identify the trend, but is there something else that you can do to this process which will make this trend go away? So the other thing that can come to mind is differencing. Let us try to see if I define another variable. So the model that we had was a random walk like this. So now what I'm doing is, I define another random variable yt. So I've defined another random variable yt, which removes the trend from my data. So what I'm doing is xt minus, this is nothing but expectation of xt. I had xn previously, but it doesn't matter. So it will just be expectation of xt here, right? Which is minus 0.2 times n. And now if you write yt, what will be yt now? So if you take expectation of yt, it will be expectation of xt minus 0.2n, which is 0 because expectation of xt is in itself 0.2n. So now you see that the expectation just became a constant, right? So we know that this random walk, which wasn't previously stationary, which exhibited a nice trend, is now a stationary process with 0. So sometimes not only doing a least square regression fit helps, but also differencing helps. So again, the next thing that you can do is, let us say we go with the actual model that we had. So it was something like xt being equal to alpha plus bt plus yt, right? Now if I use differencing, what will I have? I will write my xt minus 1 as alpha plus b t minus 1 plus yt minus 1, and now I differentiate. So basically I'm subtracting xt minus 1 from xt. So what will I get? I will get something like nabla xt, alpha minus alpha is 0, bt minus bt is 0. So I'll be left only with b here. So I'll have b here and I'll have nabla yt. And again you see, in this differenced series, the trend is gone. There is no t parameter here, right? So the trend is removed. So this is another way you can, try and experiment with the data that you have at hand. So sometimes what happens is, let's say if your trend is not a linear trend, but a quadratic trend, then you might have to take this difference twice. So it doesn't really matter much, but you are just constructing a new series. So here, this is the new series, and this series is just, difference between the value at the current time step and the difference between like basically the original observation and the observation at one previous time step. So, and again, you have to remember the fact that whenever I'm differencing, I will get one less data point. Because what happens is, let's say I have 1, 2, 3, 4 data points. So to start with, I had 1, 2, 3, 4 data points, and I'm taking difference. I'll take 2 minus 1, 3 minus 2, 4 minus 3. So I have 3 differences, but 4 of these data points. So you lose 1 data point here when you difference. So there are certain costs, but this is not much of a cost, I would say, because the kind of benefit it provides you in identifying a series which might be stationary but still be able to capture all the essence of the behavior of the time series that you want to capture. This is the best we got. So that's another method. Then there is one more method which you can use. I didn't write the name for this. So the method that we discussed was called differencing. Okay. So now sometimes, let us say I'm looking at the retail sales of Christmas trees over a year. I know that around the time of November and December, the sale is going to hike a lot. So when I plot my time series, I am going to get, let's say if I have my T here and I have my XT here, which is the sales of Christmas trees, and let us say these denote the year. So this is 1 year, this is 2nd year, and this is the 3rd year. So I know that each year I'm going to see a rise in this, and it can increase or it can decrease or it can even stay the same, right? I can have something like this. Maybe this year something else happened, but you know that there is likely to be a seasonality in the data that you have at hand. So for this kind of data sets, what you can opt to do is use seasonal differencing. So this is the third method that we're looking at. And this is known as seasonal differencing. This is similar to the differencing that we did in the previous case. But what happens is, now instead of subtracting xt minus 1 from xt, what you will do is you will subtract the next period. So what I mean by that, let me just write an example. Let us say what I have now is something like this. So I have xt here, and this is mu plus. So whenever I write a small xt, it means this is the observed xt, okay? So this is mu plus theta t plus yt. And this theta here is a periodic function. Basically, it takes similar values every period. And for now, if you're looking at the Christmas cells, let us say it is the periodic function with period as 12 time steps. So that's it. And this y again, I assume is some stationary series. Proxy for my residue. So I'm assuming that my y is stationary series. So now when I say that I'm going to take a seasonal, I'm going to use seasonal differencing to retrain my data. What in essence I'm doing is something like this. So when I write nabla here, and if I don't write anything, if I write nabla xt, this is what? This is xt minus 1. But if I write some subscript which is 12 here, what it would mean is that I'm subtracting xt, that I'm subtracting as xt minus 12 from xt. So what does this mean? When I say that I have a period of 12, I know that every November, And every December, irrespective of the year which I am in, the cells of my Christmas tree are going to be likely to be similar, right? So they are going to exhibit a similar pattern each and every month of the year. Not exactly the same, but similar for sure, yes. So what you do is, you do this kind of a seasonal differencing. And let us now write, if I apply the same thing to this model here, what I will get is, for Nebula 12 xt, I'll have to subtract xt. I'll have to first write my xt, which will be something like this. And then I have to subtract from it xt minus 12. So I'll have mu is just a constant, and theta t minus 12 plus y minus y t minus 12, right? And what will I get is, so this mu and that mu will cancel. And now what happens with theta t and theta t minus 12? So when I say that my theta is a periodic function, so let us say this is t and this is theta that I'm plotting. And I'm saying that my theta is a periodic function. So I have 12, 24, 36 here. And I know that my theta is a periodic function with period as 12 here. And if I try to plot my theta now, the kind of graph I should be expecting will be the one where I get same values of theta for each of these end periods. So I might observe something like this. So for each period, the kind of values my theta take is the same. So I know that here, this is my theta 0, this is my theta 12, this is my theta 24. So if I am at t period today and I subtract 12 from it, I know that my theta t is going to be equal to theta t minus 12. And on that basis, because my theta t is equal to theta t minus 12, which is also equal to theta t plus 12, which is also equal to theta t plus 24. As long as you're assuming that the period that you have for your data is 12. So even that would cancel out. So this would cancel and that would also cancel. And now what you're left with is yt and yt minus 12. So what you will have is yt minus 12, right? And this is nabla 12 xt. And I know that this is a stationary process. That itself is a stationary process as well. So any linear combination of those is also going to be a stationary process. So now this is a stationary process, which I can model, right? Using the models that we have studied so far. Is this making sense?
Yes, ma'am.
Yes.
Okay, good. So now let us study. So also I guess I should just mention this. Sometimes what happens is the way to recognize seasonal differencing or seasonal data that you have at hand is very easy, right? You just plot the time series and you have a look and you know that this seems like a seasonal factor is affecting the time series. And if you sometimes even try to plot the ACF, so I know that the correlation between this guy and that guy is going to be almost 1. This guy and that guy is going to be almost 1. The value theta takes here and the value theta takes here is also going to be 1. So I know that my ACF will also look something like this. So I'll have, let's say, decreasing and then it will again increase and then it will again increase. So you can have your ACFs something like this, which might indicate, that your data is of seasonal nature and you might need to employ seasonal differencing to make this data into a stationary process. So that is another concept, and sometimes you might have this, sometimes you can have something like this, which, tapers down, but then it again increases, and yeah, something like a nice wavy curve. Yeah, that's just another fact. And now let us see So this method of, seasonal differencing works well, but sometimes what you have is not a proper seasonal. So now I was trying to determine the sales of my Christmas trees every year. And I could easily guess that in November and in December, the sales are going to be higher than the rest of the time of the year. But sometimes the variable that you are trying to account or see the behavior of might not exhibit proper seasonality. But you see that there might be some patterns, some recurring nature of the data. So there is another method that you can employ, which is called method of seasonal means. So what happens here is, so again you have some data which is, seasonal in nature, and you kind of know that, the difference between the observation and the previous observation from the same season is what will not help you here. So we know that the seasonal differencing is not going to help much. So there is another method that you can do. So what you do is, again, let's say, again, you have a period of 12 and you have observed around, so you have observed some data set, and I'll just write here. So I have x1, x2 till x12, and I'm keeping this separate for reasons I'll tell you now. Let us say I have 36 data points for now. And what I'm doing is, I'm branching this off into periods of 12, because that is how the seasonality I see, So, but still there is a lot of variation within. So it doesn't need to be the case that if my sales in X12 are higher, it's going to be that high in X24. It could not be that high as well. So what you do is, you take the means. And when I'm talking about method of seasonal means, what you do is you subtract the average value over all the months. So when I talk about average value over all the months, I denote it by mu hat, and that will just be summation of xi upon 36, which is the number of months I'm looking at, right? So that will be my overall mean. And now if I have to figure out my means for each and every period, so not exactly each and every period, but each and every time step in a period. So let us say this I'm representing as 12 months. So I know that this would be my January, February. And let's say this is the year 2010, 2011, 2012, right? So what you have is January here, X13 is going to be the sales in the January, X25 is going to be the sales in the January. So if you want to figure out the average number of sales that you have had in January, you will have something like X1 plus X13 plus X25 upon 3. So that would be your average sales in January. But you know that these are going to be different. So when I'm talking about the method of seasonal means, the thing that you do is to stabilize these averages, because this can either be very high or very low depending on the kind of seasonality that you are looking at. So what you do is to stabilize these averages, you subtract from these the mu. So in essence, what you're doing is, let us say you have this data which is seasonal and you get these averages. So the average might be high, it might be low, something like this. So you gather a mean around it. This is our mu hat, and you estimate these differences. And then this is the data that you have, which you are going to model now. And next step, if you are looking at the February, you will have something like x2 plus x14 plus x26 upon 3 minus mu hat again. So this is what you do when you're talking about the method of seasonal means. And this is how a periodic function, which is theta here, will help you, to get away with the seasonality and have some data set which does not fade away the behavior that you're looking for in the time series, or let us say if you want to predict. So sometimes what you do is you convert this whole season data. No, sorry, not the season data. So season data is actually the word that is, used for a data over which you have worked and make it as good as possible to be used for a prediction. So that is called season data, but doesn't go away here. So what I was trying to say is, let us say you have some data and you observe seasonality within that data. So you remove that seasonality and then you get some data points, which if you plot look like stationary and satisfies all the tests that you can do to check the stationarity of a data. Then you will try to model that data. And after you model that data, you try to forecast something using that model, because sometimes that is what you need a model for, to forecast what's going to happen ahead. And you forecast, and then you again retransform or inverse transform and put back the seasonality in that transform data, which you have forecasted already, to get to the actual value of the data that you are interested in. This is very interesting, and this is widely applicable in all of the practices in actuarial science, statistics, or in basic forecasting, I would say. And the next method that we're going to have a look at is called, this is the last method that we have in our syllabus to remove a linear trend. So this method is known as method of moving averages. This is a pretty cool method actually. Has anyone heard of moving average before? I mean, not in terms of the models, but in terms of practice. Anyone?
Models in terms of a share price, like when you see the
Yeah.
charts of a stock, so there is some indicator known as Bollinger Band, and it indicates the moving average of the price.
That is actually the very prominent example that you always have of moving averages. So always when you try to, analyze the stock prices, you want to see what likely the price of the stock is going to be in the next time period for you to bet your money on, right? And then you try to use these moving averages to determine the average, determine the expected value that you might get of the stock the next year. And this is generally used in financial aspects a lot, more than we even imagine it to. But yeah, let's dive into the nitty-gritties of this process now. I think this is a critical process, so let us try to understand it with an example first, I would say. So what happens here is, when I'm talking about the method of moving averages, so we have y and x. Okay, so when I'm talking about the method of moving averages, let h be an integer. So I'm just writing some formalities now. I'm letting h be some integer value. And I'm defining some another random variable altogether by t, which takes this value. So this looks complicated right now, but we're going to understand this using a simple example. Let us say I have a process xt and it has realized some values. So my realizations I'm going to denote by small xt, which are just some random bunch of numbers. So I can put 5, 3, 2, 4, 5, 6, 7, 8, 3, 9. So I have this set of 10 numbers, 10 realizations of a random variable xt which I have observed. And now what I have to do is, I have to figure out a moving average. So we all know what average means, right? Average means just the expected value. But when I'm talking about moving averages, it somehow means that, we are taking average, but we are moving. So let's see how we are moving and where we are moving. So let us now see that, let's say, for h equal to 1, I'll let you guys know what this h and how, why do we have this kind of expression. But yeah, let us bear with that for now, and let us try to understand the core concept of moving average first. So let us now say that I'm looking for h equal to 1, and if I calculate my small yt's now, so I know that my yt will be what? So if I'm looking at y1, what will it be? So I have something like, so my t here is 1. So I'll have x t minus 1 summed up, where I is just minus 1 to 1. But I know that I only have 1 to 10 values, right? I don't have any value for like minus 1. So what I can do is, let us put a question mark here and we'll see what we can do for it the next time. Okay, so let's get ahead for the next times. And let us say I have y2. So now what I will be summing up is, so what I'll be summing up over here, yeah, this should be j. Okay, yeah, good. So I'll have xt minus 1, x0, and x1 here. Sorry, I'll have xt minus 1, xt, and xt plus 1 there for y1. But for y2, so if I'm looking at this 3 guy here, I know that I have something at, so this is my t here. So this is my t, which is 2 here, and over here my t was 1. So I know that I don't have any value for x minus 1, sorry, for x0 here. And what I can do is, let's say if I have y2, so I know that my, I can maybe write it for here. So I have my t is equal to 2 here, and what I'm looking at is summation j going from minus 1 to 1, x2 minus j. So this will be what? x2 minus of minus 1 will be what? Plus 1, x3 plus, then j will take 0, so this will be x2, and then j is going to take the value 1, so it will be x1, right? So I have x3 plus x2 plus x1, and I know that my 2h plus 1 is just 3. So what I can do is, my x1 is what? 5. 3 and 2 simultaneously, so I'll take 2 plus. Is this clear to everyone? What did I just do here? So I'm taking a moving average. Now, when I'm writing y3, the values that I'm going to take will be 2, 4, and 5 upon 3, and so on till I have y9. So for y9, which is here, I'll have 8, 3 plus 9. So I'm taking 8 plus 3 plus 9, 1 upon 3. And I'll get some values for these guys. But what about y1 and y10? For y1, we only have 5 and 3 values, right? We don't have anything for x0. And here for y10, we only have values for x9 and x10. We have nothing for x11. So sometimes, like, this depends on you as a researcher, what you want to do or what your best guess is. So sometimes what you do is, you just assume. So you just assume that my x0 is going to be similar to what my x1 is, which here is 5. And you assume that my x11 is going to be exactly what my x10 is, which is 9. So in that case, for y1, the average that you will be looking at will be 5 plus 5 plus 3 upon 3. And here you will be looking at 3 plus 9 plus 9 upon 3. And you see how I'm moving across time, but I'm still taking the averages. So first I took the average of something like this. Then I'm taking the average of these guys. Then I take the average of these guys. And I'm moving, but I'm still taking averages. And that is how you have the name moving averages. And this is the method of moving average. And this is actually what you do when you're, trying to take these averages. And now I'm going to write the extended equation, which you will generally see for use in your textbooks, I would say. And that looks quite daunting, but in process, this is just bacha type. Addition karo, divide karo, average lo, khatam kaam. Okay, so let us see how we can write this. So now what happens is, whenever I try to, decide what my H will be or what my D is going to be. So I haven't yet introduced D for you guys, right? So if I go according to, the definition that is there in your book. So what we are doing is we are using a simple linear filter to convert the process that we have at hand into a process which is something like this. So this is the converted process and this is the process that we started off with. And sometimes this xt minus j will come with a coefficient here. So it might have some coefficient here, may not have some coefficient there. So the kind of filter that you have applied here with this summation is the linear filter, which allows you to eliminate the effects of some variation, be it periodic in this case, to eliminate. And now let us say I have some data. So let me just write this down first. I would say it's a pretty big equation. Oh, let us do this for. So the thing that we just saw was yt was always equal to 1 upon 3 xt minus 1 plus xt plus 1, right? This is what we just did. So what happens is you always want to have symmetric averages. You always want to look at a symmetric time period. And what you do is you start off at 0. So let us say we are interested, let us say we are taking a 7-point average. So if I say that I want to take a 7-point average, that I want to have 7 points in each average that I'm taking, what I will look at is, I look at -3, -2, -1, 0, 1, 2, and 3. So I know that if I go here or if I go here, I'm observing the symmetricity in the time so that the lags value are the same if I start from the center here. So, and that is what we are interested in. And this, because this is the time when my G takes the value 0, right? And that is why we call it average as well, because ultimately when we take the average of this, it's most likely going to be centered around here, like not exactly, but we hope it will be. So we, in the hopes of, just making it symmetric. So it's easier if you are looking at the odd value. So here we were looking at a 7-point average. But what if I want to look at a 4-point average? What can I do? So if I want to look at a 4-point average, what I will do is, I want all of the time periods. So when I talk about, a periodicity, so if I have a periodicity in my data, what I will have is, if I want to look at a 4-point average, I know that I only should have 4 data points. So what I can do is, let's say I start with 0. I have -1 and I have 1 here. I have my 3 data points. Which one should be the 4th one? Should I add -2 here or should I add 2 here? So what you do is, you add both of these and you divide them by 2. So not exactly that, maybe I shouldn't even write that. So you don't divide the time period by 2, but what you want is, you just want each period to be represented equally. And that is the reason what you do is, you take both of these -2 and 2 into account, but the data value here and there might just be divided by 2 to make their sums as 1. So in effect, what you are trying to have on the average is, not distorted by this -2's value or this 2's value if you choose any one amongst those. And that is the reason. So this will be the case if you are looking at any odd point average. But now let's say if I'm looking at something for even, what I will have is yt as 1 upon 2h. And remember the half I just spoke about, because I'm looking at even. So this is for the even. And again, I will only have 2h here if I'm looking at the even case. And if I'm looking at the odd case, I have 2h plus 1. So here my h is just 1. And here my h is just 1 if I'm looking at 2-point average. But if I'm looking at 4-point average, this h will be 2. So I'll just have half of xt minus h plus xt minus h plus 1. And you will somewhere have xt minus 1. And then you will have xt. So this is my 0 time, right? Where my j takes the value 0. And here my j takes the value minus 1. And here my j will take the value 1. So remember, when I say all of these values for j, I'm always summing my j from minus h to plus h. And now I will have this up until x t plus h, which will be divided by half. I should just write x t plus h minus 1 for completeness sake. And I'll just complete my bracket here. So what happens is, this kind of a representation ensures that each of my periods will make equal contribution to the average value of the whole period that I'm looking at. The whole set of the average that I'm looking at, not period. Right? So now let us say if you have a yearly data and if you have a quarterly data and the period is 1 year, so what will you have? So you have 1 year of time. So let's say you're looking at 1 year and you have quarterly data. So in 1 year, we know that we have 4 quarters. So that is what I'm going to denote as D here. And if I have the even period, my D is going to be 2H. So it is just what I divide this with. And here my D is going to be 2H plus 1. So when I'm looking at the quarterly data, I know that the times I'm observing the data is 4. So in that way, if I equate this to 2H, I get my value for H is 2, right? And then you can just substitute this values here and you will get what average you have to look at for each moving average that you want to figure out. And because the very fact that you're interested in the center value, this is known as centered moving average and also symmetric moving average. And there can be other kinds of averages as well, like you need not always have 1 as the coefficients for all of these values, but this is just what we are assuming. We are willing and we are making sure that each period has an equal contribution to YT, and that is why we have taken something like that. But for other purposes that might change, and for the model that you have at hand, you have to make the best guess as a researcher as to what kind of coefficients your linear filter must have for it to give you a nice moving average. And that takes a lot of trial and error. And you have computers, so you don't have to worry about all of the technical details. The computer will do it for you easily. And this is actually one of the methods which is known as filtering techniques, and because that helps to clear the variation that you have in the data. So let's say if you have some rapid fluctuations in the data, then you take the average and that will smooth the data and attenuate the noise. So that's the last method that we have in trying to remove the linear trend. So now let us see what happens if you have a non-linear trend. So when I'm talking about non-linear trend, what kind of trends come to you guys' mind? Any example that I can have for non-linear trend? Come on, there are so many examples. Anyone? Hello.
Rainfall throughout the year.
I couldn't hear you well. Can you say that again?
Rainfall throughout the year.
Rainfall of the year. Oh, so I'm not meaning, as in the terms of variables, just in terms of maths. So the kind of examples I was expecting, like, I mean, I'm not sure if rainfall has a nonlinear, but I would guess, with the fact that all of the weather data exhibits some nonlinear trend, we can actually see that rainfall might have some quadratic kind of a data. So that would not be linear, right? And if let's say we are trying to model the cases of coronavirus, it certainly does have an exponential trend, right? So that is certainly not linear. So the very first method that we are looking at, transform a process which has a nonlinear trend into something which is stationary, is transformation of the data. And the very basic example that we can have is, let us say if you have an exponential data, just apply logarithm to all of its values. And the next that you will get is the process which would have its exponential growth removed. So this is generally used in economics. Let's say if you're looking at the employment data, you generally take log values, or if you're looking at the growth rate of countries, you look at the logs of these, because log of difference has a nice connection with the percentiles and the percentages. So it gives you a nice information and readily available to interpretation kind of information for the data set. So a simple transformation as defining another random variable, which is just log of xt. That's it. This is a very simple case. Now the next step, I think this, I really like this transformation. It is known as variance stabilizing transformation. When you're looking at this kind of a transformation, what happens is you have a variance. So my variance of the data that I'm looking at X is somehow proportional to my mu. And mu is the mean of the data. So this is my mean of X. So let us say my variance of X is some function of the data. So the function I'm just denoting by h. And that is what creates the disturbance in the data that you're looking at. So this generally happens in the case of Poisson, where you know that the value of mean and variance is exactly the same. So if your mean changes, you know that the variance is also going to change. The variance is not stable, either is the mean. So what can you do in those sort of cases? And there is some transformation that you can do. So what there is actually one formula, very nice formula for this, and this is assuming that let me just put the heading, I guess. So one of the things that you can do is to have a look at the relative variance. So maybe first example is something like relative variance. Now what do I mean by relative variance? Let me explain. So what I have is, let us say the way my mean is connected with the variance is like this. So this is my variance, and I know that mu u here is my mean. So my variance is just s square times u square, where s is just some sort of a coefficient. So now what you do is you define another variable. You define some another variable y, which you integrate over x, and you have the square root of the relationship, the variance that you have here, and with respect to du. So let's say if I have s square u square here, what will I have for y? So here my y will be integration over x 1 upon square root of s square u square du, which will be what? Integration of x, s can be taken out, 1 upon u du, which will be what? S times log of x, right? Not exactly like, I should be pedantic. So I'll have s log of x, ln of x, right? And this will be my y. So I know that my y, oh, s is in the denominator here, right? So this should be 1 upon s raised to minus 1. So I have my y equal to s raised to minus 1 ln x. And I can easily see that my y is proportional to the log of x. So I can just rewrite that my y will be proportional to log of x. And this is the kind of transformation that I can use to stabilize the variance of the series that I'm looking at. So this is just one of the transformations that you can do, which is known as relative variance. And the transformation that you just did will be called logarithmic transformation. And then by doing this transformation, you remove, the effects of varying variance and you stabilize your variance. And now this is, so also why are we doing this transformation? We want our data to be stationary, right? So that we can model it and we can forecast it. And the main parameters for any series to be stationary is that it should be kind of linear. It should behave normally, and it should have constant mean and variance and all this sort of stuff. So this kind of transformations will give you those kind of series that you're looking for. And there exist other couple of transformations as well. So now the syllabus has been altered, but when CS2 was CT6, they had this whole chapter on generalized least squares where we used Box-Cox transformation, and that is generally used to have to convert something into a linear series. And generally if I think it was something like ensemble transformation which you use to convert a Poisson type of this into a Gaussian. So if you are looking for some kind of transformations to have a look at, you might want to check those up, and those really do well. So here for relative variance, we used y as log x, and for Poisson case, what generally happens is you use y as the square root of the x, and that is what has been proven to work the best. So that was the second method of trying to get what we want, and the third method is, I think maybe I can just put it over here. It is called transformation to increase the normality. So when I'm looking at any data which I want to be stationary, sometimes what happens is the error terms, because all of the models that we have studied so far yet do assume that my error terms, that the residuals that I have are normally distributed. But what if they are not normally distributed? So that would create some doubts, as to whether the standard practices that you have yet learned are even applicable or not to model the data in the way we do. So what happens is you will have some sort of processes which will check the normality of the error terms, and then there is some transformation that you can do on that data set to make it look like a normal, so that there is some stability in the variance, which is like sigma square, just a constant, rather than it being dependent on the t and varying with respect to time. So sometimes what happens is there can be a bias in the data, because sometimes if you are looking at a data set where indeed the variance is increased, and if you assume that I want to use the methods that I have learned to model this process, you might be taking away the whole uniqueness of that data set. So you have to take into consideration the biases which might creep in when you are trying to model some series that you have at hand. So we have learned all of these techniques, and now we know that we have this tools with us, and given any time series, I can now perform a time series analysis. But you're farther from the truth, because the kind of techniques that you have to use depends so much on the kind of time series that you are given. And also as a researcher, you have to make calls and judgments and which kind of techniques will be best suited to the model that you have. So there is something known as back testing, which is generally used. So you can do back testing where let's say you have some data set. Let's say you have 1024 data points, and what you do is you only use 1,000 of those data points to model, and then you test your model by predicting the next 24 steps that will have. So you already know the values of those 24, and you check out the difference between those, and then you try and check, and then you try and use the model which will best approximate those 24 values, so as to know which model works the best. And that takes a whole lot of trial and error, and it takes you days, months to realize which model is the best model, what kind of parameters should you add, how many parameters should you have, and all this sort of stuff. So let us look at, so these were the techniques actually to convert a non-stationary time series into a series which we can use the techniques that we have learned so far on. So now we will try, so from now onwards, I'm going to assume that the series that I have at hand is a stationary series, and I'm just going to use the methods that we have learned. So let us see, how do we identify the models, the moving average models and the AR autoregressive models that we have. Okay, so remember when we studied AR models and MA models, we did have a look at their autocorrelation functions and the partial autocorrelation functions, right? So, and we also know that if I'm looking at the AR process, I will have a geometrically declining ACF. But if I have a ARP process, my PACF for all the values, all the values of lag greater than P is going to be 0. And the opposite holds true for the moving average process with order Q. So if I look at the ACF, it will cut off at lag Q, and then it is just going to take the value 0. And if I look at the PACF for my MA process, it is going to geometrically steadily decline, but never reach 0. So the best way to see if the model that we have at hand is either a MA or AR is to plot their ACF and PACF. So when I'm using the data that I have at hand, I'm in actual estimating the sample ACF and the sample PACF. So remember, whenever you do any kind of analysis, now you are going to have this nice little hat on the top of your estimator. So let us put that. So let's say if you want to figure out the mean, and let me define my data set first. So you have x1, x2 up until xn. So the estimate for mean is going to be just 1 upon n summation of all of these xt's, right? Where t takes values from 1 to n. And now if you want to figure out the autocovariance, so for autocovariance, this was how I denote my population autocovariance. But to estimate it, you use the sample autocovariance function, which is sometimes denoted as, that would seem like I'm multiplying, but, or I don't know, I maybe shouldn't write that. So it is also denoted sometimes as CK. I can write it like this, yeah. So this is my sample ACF. Okay, and when I'm writing its function, I will write something like 1 upon n. So we have n data points summing across, where my t takes values k plus 1 till n. And I have xt minus mu hat and xt minus k minus mu hat. So generally, even while I was studying this concept, I had this doubt, why do we not start from k and why do we have to start from k plus 1? Can anyone see? Why should we start from k plus 1 and not k? So the lag that I'm looking at is in fact k, right? So why shouldn't I start looking from the lag k itself? So let's see what happens if I put the lag k. So if I have lag k here instead of k plus 1, I will get something here as x0, which I have no value for accounted, right? So remember, whenever you take differences or whenever you're trying to take two realizations into account, you are going to lose out some data points. So you cannot possibly have a value for x0, and which is why you take this t starting from k plus 1 to n. So then the next function is the autocorrelation. So this is not sample ACF, sorry. This is autocovariance function. And now I will write my sample ACF. It's pretty confusing because ACF can stand for autocorrelation function and autocovariance function as well. But ACF is written only for autocorrelation function. And this sample ACF will be denoted by RK. So this is going to be gamma k upon gamma 0 with little hats, right? So I hope that's clear, and that's it. So this is how you will estimate, and this is just not some technical stuff now, that if you are looking at kth lag, you know that you are going to have only, in a sense, n minus k variables here, n minus k sums here, because you're looking at n, but you're starting from k plus 1, not from 1. So you are ignoring all the values which are below this, which are k values. So you should, in essence, write, divide this by n minus k, but that is actually going to give you an unbiased estimator. So let's say if you were to know the value of the mean, then if you divide the estimator with n minus k, it would give you an unbiased estimator. But this is generally the case which is used in practice as well, and it doesn't make much difference because it is generally observed that, so yes, let me just finish my first sentence. So if you just observe this at smaller lag values, so for the values where my k is going to be lower, I know that my n minus k is going to be as closer to n as possible, so it wouldn't make much difference, and it's negligible anyways. But also there is one theoretical reason why we can take this n here instead of n minus k. So even though if I use n minus k, maybe let me write this. So if I use n minus k, I get an unbiased estimator. But the variance of this estimator will have been increased. So generally there is this mean variance trade-off. So what you look at is MSE. This is mean squared error. And the formula for MSE is something like, I guess, bias squared plus variance. So for 1 upon n type of an estimator, so if you have 1 upon n, you get a smaller MSE. You also don't want to have a higher variance just so that you can use an unbiased estimator. So there is this trade-off, and you try to have as lower value for this MSE as possible. And 1 upon n gives you the smallest MSE. So that is why in practical as well, people go with this small MSE. Yeah. Is that clear? Does this make sense?
Yes.
So now you know how to estimate this. Sorry. So now you know how to estimate these sample ACFs and sample PACF as well, right? So for PACF, you will just have to use these RKs, and you can easily derive the PACF. So for PACFs, it will just be this. I guess they use, yeah, it's the same denotation. So yeah, for sample PACF, you will use this, And actually, there's a formula which I never discussed previously, I guess. So you take two matrices, one of it is in the numerator and the other one is in the denominator to figure out this and write a common function for this. But it's given in the tables and you do not have to, worry about knowing that now. So this is how you know once you estimate your ACF and PACFs, and then you can plot them and you can identify easily by where the ACF or the PACF cuts off for AR and MA models. So I hope this is really interesting. Is this sounding fun to you guys? Like, I don't know, but this is actually a pretty cool concept because if you go into, if you get your hands dirty with some data set, this is really fun because R has got nice libraries and you can easily plot the routes and you can check whether your time series is stationary or not, depending on whether the route lies within the circle. So inverse lies within the circle or not. And yeah, and you don't even have to, give formulas. You just have to know the functions and that's it. So there is this nice function known as auto arima, which directly fits the arima model to your data set. And also, if you just write arima, auto arima fit, it will give you a nice graph with this two circles for AR and MA, and then you can see if the roads lie within the circle or outside the circle, and that circle will be of unit radius. So I think that's something really nice. And now let us see how to identify a white noise process. So once you have the model in hand, you also know that the error that you have in the model shouldn't have any peculiarities. So let's say you have a model, you modeled something and you figure out that it was a AR1 process, and then you try to plot its residual and you got something like this. So you have these data points and this is the residual that you have. So you clearly know that there is still some relationship within the data that you have missed, which should be accounted for. And clearly, this seems like there is some quadratic trend going on in the residuals, and you do not want that. You always want your residuals to follow a white noise process, and they should be independent of each other, if not identical. And that's it. They should be identically distributed with normal distribution, possibly 0,1. So that is why we often want to, introduce transformations that will reduce series to white noise. And let us look at how can we do that. So again, here I'm going to discuss some asymptotic distributions. So whenever I say, I think you guys must have studied the central limit theorem, right? I think we have even discussed that before in the course. So in the central limit theorem, I know that my n tends to infinity. It is never equal to some number or equal to infinity, right? So I know that I'm looking at the asymptotic distribution of this random variable, and that is the same thing that you're going to do here. So you want your residuals to form a white noise process, which will help you to verify whether the model that you have fitted is indeed, a best model for the data that you have at hand. So there is some asymptotic result, which I'm not going to give you guys the proof of. The proof is very tedious and you need to know the matrices and all this sort of stuff, but it's interesting nevertheless. So let us try to, so the thing that we're doing is identifying the white noise. Okay, so now I'm giving you the original model that I have. So let us say I have an original model, which is something like this. There is just a mean, and then I have this. So now what you do is, okay, so also tell me one thing. I want my residuals to take as minimum value as possible. So the best case scenario will be for all of my residuals to take a value of 0, right? So that there is no error in the model. Whatever the variables that I have taken as my predicting variables into determining the dependent variable will account for all of the variation that I see in the data, and there is nothing left for the residual. So I want that, all of my residuals to take a value of 0. But we know that that is not possible and that is not the case. So now what you have to do is, we can't, really see that my errors should be 0. So we provide some interval that if my errors lie within this and that interval, then those will be of acceptable nature to be classified as a white noise. So now what you do is, you have your ACF and PACF. So you approximate those to some distributions, and what you get is that your RK, which is the sample ACF, follows normal distribution, and when I'm writing two dots here, it just means approximately, and for the large samples, so this is true asymptotically. Maybe I should write, we're looking at asymptotic and for large samples. These are the two assumptions that we have made. So this follows normal with mean 0 and variance 1 upon n. And it is also observed that my sample PACF also follows the same. So now what you will do is, you will figure out some confidence intervals for the variances of these guys. And if your sample ACF or sample PACF falls outside that range, then you will say that, that model that I am looking at doesn't have a white noise. So let us have a look. So if you are looking at 95% confidence interval, so I know the value of that will be 1.96. So what I will do is, I will have a range for my variance. So it will be something like -2 upon square root of n, because the mean is 0 here. So -2 upon square root of n and 2 upon square root of n. So in your book, they have just approximated this to 2 instead of 1.96. But it's equally well if you write 1.96. In fact, it will be more accurate. But just for standardized purposes, what you have taken here is 2. So if my sample ACF or my sample PACF lies outside this range, my model isn't a white noise. Okay, so you generally have, so when I'm talking about these ranges, let's say this is 0, this is the line for 0. So what you will have is some sort of, an interval. So this might be the interval. And if at all your ACF lies beyond this interval, then it is not going to be, I'm just plotting randomly now. Yeah. So now you have these and these and these lines beyond this interval that you have defined, right? Which is -2 upon square root of n and those. So this clearly is not a white noise. So that's it. And this is actually one of the methods for you to figure out. But again, there is a caveat, right? Because we were looking at this 95% confidence interval, I know that I should expect at least 5%. So at least 5% of my observations can lie outside the range. So if I have 20, so let's say if I'm looking at 20 observations, then if I'm looking at 20 lags, then I can say that 5% of those 20, which is just 1. So one of the lags can exceed the perimeter that I have defined for this interval, prediction interval. And if you only have one of those lines outside, then you can still say that this is a white noise process, because you cannot be sure if that 1%, if that one line which you have outside this interval is actually one of the 5% ones or the 95% ones. So that's the case, and that is how, somewhat there is a discrepancy again. So I don't know if you guys know this or not, but there was one psychology journal which banned the use of p-values because of the distortion and because of the discrepancy that there was in their explanation and inference for that matter. I might share, I think I have the PDF of that still now. And I actually got to know this by reading somewhere on the blog of Andrew Gelman. So I don't know if I'm pronouncing his name correct or not, but there is this guy Andrew, and he actually posted on one of his blogs, which is about econometrics and statistics and mathematics. And it was really heartbreaking for me to know, the stuff that actually helps us to realize something. And almost all of the papers widely use p-values to produce results which are significant or not, and even see whether the model works or not. So turns out you can hack your p-value. So there is a paper also titled Hacking the P-Value, and it's pretty cool actually. Statistics. I guess you guys must have seen the book, right? How to Lie with Statistics. And yeah, I think studying statistics makes you a humble person, because you're aware, of all these things that you can do and all these possibilities that exist beyond the realm of what even is in control of you. So, I don't know, this is going on. So let us come back to the study. And this is just one of the tests that you can do to identify whether the series at hand is a white noise or not. So the next test is actually the portmanteau test. So let me write it first. The spelling is pretty nice. So yeah, this is just. So there is a test known as portmanteau test, which was actually introduced by these two guys known as Yoon and Box. And they have this test statistic where again you are going to use p-values to determine whether it's significant or not enough to determine if there is some correlation between the data that you have, which should ideally be zero if you're looking at a white noise process. So the test statistic for this is, it's generally denoted by Q, and they write it as n times n plus 2. So it is m lags that you're looking at, and this is r k squared upon n minus k. That's the test statistic that you have. So this is used, to check the autocorrelation within the data set that you have again. And it fits our purpose because we will expect that there is no autocorrelation in the data if I'm looking at a white noise process. So the uses of this portmanteau test goes much more beyond, just identifying whether we are looking at a white noise or not. But we can use one of these tests as an indicator if there is any correlation within the residues or not. And now if you want to determine its statistical significance, we know that we just compare it to a chi-square m. So if I'm looking at m lagged values, I will have chi-square m here. And let us say if you have a raw model where you haven't yet, modeled any parameters, then the degrees of freedom will be m. But if you have modeled a series and let's say you have some ARMA model with some ARIMA model, let's say with some P, Q, and 0. So what the degrees of freedom will be something like this. You will have to subtract, the number of parameters you estimate. And then you guys are aware, how to compare this to say what's going to happen. So in this test, if you have a smaller p-value, so the smaller the p-value, the significant autocorrelation will be. So what you will have now is, I think, so there is one example given after this in your books, which I think it's pretty straightforward. So you can do that on your own. I was supposed to discuss it, but I'm now, not in the mood to discuss that. And I think you all can see. So what they have done is they will give you some values for R. So let's say if you're looking till lag 6. So you will be given values of R1, R2, R3, R4, R5, and R6. And then you have to use this portmanteau test to determine whether this data can be considered as a white noise or not. And it's pretty straightforward. So now let us look at the actual process of identifying whether we have a MAQ or not. So when I'm talking about, identifying a MAQ process, what happens is we have already seen this and I've already discussed this, but let me just write it again. So identifying MAQ and ARP process. Okay. So whenever I have a MAQ process, I know that my ACF is going to be like what? Can anyone remind me?
It will.
I couldn't hear you properly.
The ACF will cut off and become 0 at some.
Right? So if I'm talking about ACF, it will cut off and become 0. And here it is just going to geometrically decline. And then if, let's say I'm talking about the PACF, here it will geometrically decline. And here it's gonna cut off to 0 for k greater than p. And for k greater than q. All right. And there is some nice formula given for the variance of this MAQ models RK, which is the autocorrelation, which you can sort of ignore, but let me just, write it down for the sake of completeness. So my RK here is going to follow approximate normal distribution. Again, the mean is 0 because in MA you only have the error terms, right? So you want them to be 0, but here you have something like this. Yeah. Last bracket. Good. So I know here that my rho k is 0 for these cases, and for my AR model, I know that my phi hat k is going to be 0 for all the times where my k is greater than p. And here if I see my partial autocorrelation function follows normal distribution with 0 and 1 upon n. So again, if you have a look at the confidence intervals for these guys, remember to use this variance for MA, and that will be the variance for AR model. And that would finish off our process to identify this moving average processes or AR processes. And now we will have a look at what happens if you don't have either a pure MA or a pure AR process. What happens if you have a mixture of both ARMA or something else? So let us see. And now is the time, this is actually called as Box-Jenkins methodology, and all the techniques and tools that we have yet learned are a part of those 3 processes or 3 steps that you do to forecast something. So let me just summarize that for a while now. So I haven't actually checked whether this box is the same as the box I'm going to talk about now, but there was this British statistician named George Box who actually said that all models are wrong, but some are useful, and we have to figure out what is the best that you can do. And actually, one of my professors at the LSE, he used to say, if you want to model the reality, then just look outside the window. You don't have to use these tools and techniques. And we know that all of the models that we are going to fit will have some sort of lacuna or the other, and they won't be able to have the accurate description of the reality, but they will give you the best approximation that will do your work. And sometimes you don't have to look at all of those complex data. You just want to figure out if there's a relationship between inflation and the unemployment. Is there any effect of the prices on the way the people spend? And you kind of have to ignore some other aspects, and you have to sometimes take into consideration those complexity as well. And there have been various techniques used for that, but still you can never be sure. You can never say anything with 100% certainty, okay, that this is what's going to happen in the future, because we all know that the future is uncertain. And it was, I guess, by Laplace. So he actually has this nice quote, which I don't remember now, but I might just share it up on the Google Classroom for you guys to have a look. That under what circumstances you can actually predict 100% accurately what's going to happen next. And we know that that's never going to happen. So those conditions are like just utopian conditions. So yeah, I guess that's a pretty good premise to start by knowing, the difficulties that we have at hand. But still, we got to do our best, I guess. So this is what we have, a methodology by Box and Jenkins, and that will provide us sufficiently accurate description of the behavior of the historical data to quote your books. And there are 3 main steps in this. So the first is you identify what model you have. So you identify the model. And to take into all of the things that can happen, you look at the ARIMA model. And with some P, D, and Q. And once you have, figured out what your P, Q, and D should be, then you look at the estimation of the parameters. So then you will identify the alpha and the betas, which are the coefficients of the lagged values of X's and the lagged value of white noise. So then you estimate the parameters. In the model that you have just, identified. And now once you have estimated the parameters, this is the last step, which is very, very important. It's called diagnostic checks. Whether the model that you have fitted capture the behavior that you wanted to. Is it ill-fitted? Is it over-fitted? Or is there some other problem that you might have in the model that you have fitted? That would all be verified when you do diagnostic checks. So I think it's 3:40. And should we take a break now before we start off with this methodology? I think yes, we should probably take a break now. And then let's have a 10 minutes or 15 minutes break. So we'll start again at, let us have a 20-minute break. I think it's a lot that we have done today. So we'll start again at 4 o'clock. Does that sound good?
Yes.
So I hope you guys are excited to study Box-Jenkins methodology. So I'll see you guys at 4 and enjoy till then. So yeah, I'll see if I can, maybe.